Welcome to the morning session. Our first talk is by Professor Balasubramanian, and he will continue his lecture series about the circle method.
Yes, okay. Let us first of all recall what we have been doing so far. We have Waring's problem, and where we had looked at this and wrote it as a major arc and minor arc. And then we found out the major arc contribution is something like a singular integral which is bigger than n power sk minus 1, which I will write as p power s minus k. And this is positive if local conditions are satisfied. And remember, my f alpha is equal to summation n m not exceeding p e of alpha m power k. Therefore, you see your f alpha, the trivial estimate is p, but I am interested in the lower bound, and therefore I can't take the trivial estimate. When I take the lower bound, I have to take the fluctuation into considerations. And when you lose a fluctuation into consideration, I seem to lose a p power k. And I lose a p power k, and therefore in the minor arc, I am supposed to save a p power k. A k and probably a little more is what I need. Okay? And then we said Hua's lemma essentially saves you the k, and Wales estimate saves you the little delta which you want. Okay? Because the Hua saves a k in the 2 power k estimates, and Whale saves an amount 1 over 2 power k minus 1. And therefore, if your power is bigger than 2 power k, then you can use both of them. Use the 2kth power essentially to save a k, and the rest, at least one more power, to save a 1 over 2 minus. And then we said Goldbach, which we said again the same thing, 0 to 1, f alpha. I am starting to f alpha cube now, e power minus n alpha d alpha. I am only looking at the ternary Goldbach, because I want to say where is a problem which comes in the binary Goldbach, where you will have a difficulty, where this f of alpha is equal to summation log p e power minus p alpha, p less than or equal to n, and the major arc is a summation q less than or equal to p summation over a ma q. And this p is only a power of log n. And this p is only a power of log n because for sigma log p, we do not have an asymptotic formula once your p is bigger than power of log n. Okay? This was something which was commented upon yesterday also in that lecture. Okay? That you have an asymptotic formula only when p is less than or equal to log n. And then we did the major arc. And the major arc was essentially Jn into Jn. And this singular integral is bigger than or equal to p square. And this Gn is bigger than positive if it is local. Under the local condition, that is, and we even saw the local condition. There was a product p1 minus 1 over p minus 1 whole square in the main term, and 1 minus 1 over p minus 1 whole square will of course vanish when p equal to 2. But this product occurs only when p does not divide n, and therefore you have to bow. Therefore, when it's even it will be 0, but when it is odd, it will be Good, so far so good. And now what we need is essentially, therefore, exactly the trivial estimate is, of course, f alpha is n, and therefore the trivial estimate is n cube. But in the major arc already, we have lost 1 n. In the major arc already we have lost 1 n. And what we need is to somehow gain that 1 power of n and a little more. Good? That's all. Therefore, now we know what is a aim. In the minor arc, you should 2, and then it should be in fact little more. That's what you want. Okay, because the major arc is n square, and therefore the minor arc you should say only can have only n square and a little more. Okay, in other words, essentially what we are interested is in the minor arc of mod f alpha whole cube. D alpha is little of n square. And exactly what we did in the Wales estimate, we should also have an L infinity estimate and also an LP estimate. And the LP estimate will give you something like in Hua's lemma, and the L infinity estimate will give a saving, and then you should be happy. It's okay? And now what is load? The L infinity estimate, there in Wales thing, we gained a power of n, even though a small power of n p power 1 over 2, 1 by 2 power k minus 1. Therefore, over the trivial estimate p, we gained a 1 by 2 power k minus 1. But in this particular case, we do not even know how to save any power of n. Okay? And therefore, in this particular case, we will be saving at most a power of log n. And we have to manage with that. Okay? Which means that one probably you can take the power of log n, and then from the rest you have to do. And then it is known, not only in the minor arc, even if you take the full one, even if you take the full integral, it is known that this is O of n square, this normally goes by the name Parseval's identity. O of n by Parseval's identity. Okay? Sorry? N log n? No. This O of n. Yeah, why is it O of n? Okay. F alpha is equal to summation log p e minus p alpha, p less than or equal to n. Let's say p1. This is my f alpha, and I am going to write f bar alpha, which is summation log p2 e p2 alpha. And then I have to multiply both. Now let's say p2 less than or equal to n. And then you have a d alpha, and then you have a 0 to 1. Okay? And this integral survives only when p1 equal to p2. Because this is nothing but summation over p1, summation over p2, summation log p1, log p2, integral 0 to 1, e of p1, p2 minus p1 into alpha, d alpha. And E of P2 minus P1 into alpha d alpha is equal to exactly equal to 1 if P1 equal to P2 and 0 otherwise. And therefore here only P1 equal to P2 survives. Therefore, essentially a P into a log square P. Oh, that's what you mean. And this would give you something like a O of N log. Sigma log P will give you N, and then you have. Okay? And now essentially you are happy. You are through. You are through essentially because now in order to do this integral, you take one F alpha outside, and that gives you a N over log N power 50. And then you extend. And therefore, this gives you another N log N, and totally you get O of N over log N power 49, which is smaller than the major arc. Okay? Therefore, essentially, in some sense, the Parseval saves you already a power 1 power, which is good enough, which we didn't really bother about in the Waring's problem, essentially because you have to save a power of k, and the saving power of 1 doesn't do good. But on the other hand, this idea itself can be slightly modified, as was done by Davenport, to really get to the advantage from the Parseval's formula. Okay, which we will do possible tomorrow. Is it okay? And this is exactly now what we want to prove. And we will prove that. And before proving that, now I can probably tell you where I get into problem when I want to do the binary. In binary, the same thing is true. You will start with the 0 to 1 f alpha whole square e power minus n alpha d alpha. And again approximate f alpha exactly as you did in ternary. And then you will get a singular series, sometimes a singular integral. And assuming that your n is even, the singular integral will not, singular series will not vanish. And the singular integral will lose exactly 1 power of n, exactly as in that case. You will lose exactly 1 power of n. And therefore, in the minor arc, you have to save 1 power plus a little more. If you can save 1 power and a little more, then it's fine. Okay? But therefore, what is that you have to prove? You have to prove somehow that 0 by over the minor arc, mod f alpha whole square d alpha is a little of n square is what you have to. And now again, you can use Parseval to get 1 power of n, save a power of n. And then after using the Parseval, there is no more power left for you to save anything more. You have only power 2. Okay? On the other hand, trying to do anything with the L infinity norm is completely useless, essentially because we know that in L infinity norm, we can only save a power of log n and nothing. Okay? Yeah, little of n, sorry. Okay, therefore 1 power of n we have to say the L infinity norm, therefore you see here you have a power 3. And since you have a power 3, you can use a power 2 to use a Parseval to save a power. And then the third power, you can use the L infinity norm to save a log n, which is not something which you can do in the Goldbach. Is that okay? And now this is a result due to Vinogad Rao is what we are going to prove now. And this is something which is useful in many, many contexts. And therefore, let's do that. Okay. Therefore, now what is the situation now? That we are now trying to estimate summation p less than or equal to n log p e of p alpha. This is what we want to estimate. And we saw that the log p is, of course, completely harmless. Therefore, that's not a problem. And this e of p power alpha is linear in p. We saw yesterday that if you have a linearity as well as you summing over an interval, you can gain something because of the fact that it is a geometric progression. And here, the problem is that the sum is not over an interval. Okay? Since it's not over an interval, it cannot be viewed as a geometric progression. Therefore, how do we do that? Okay? And this is what Vinogradov did and managed it. And these ideas were much later, much simplified by Professor R.C. Vaughan, Robert Vaughan, which goes by the name of Vaughan's identity. And that's exactly what we are going to study now. What is Vaughan's identity and how does it help really to do that? Is it okay? Okay, before that, let me make one more comment which I will be needing. We proved that when we have okay, I have an alpha and I will always assume that alpha minus a over q is less or equal to 1 over q square. And again, the major arc in this problem was like that. And we defined the minor arc as the rest, but then we found that it is probably slightly advantage to define the minor arc also in a positive way. Okay? And whatever we did, we can continue this, which means essentially if alpha belongs to minor arc, I can assume that q is bigger than or equal to p. Because the q less than p would have gone to the major arc. Okay, that's one thing. We already saw that if you have an interval of length q by 2, then minimum of a and 1 over alpha n would be less than or equal to a plus q log q. But in this, you will get things like a minimum of a over n into 1 by alpha n. And I sort of leave it to you to prove that this will be something like an a over 2 plus q log q. The proof is exactly, essentially the same as what we did, that in every such interval, this is over q by 2, and therefore, okay, and then you will have a into y over q, and this into y over q plus o. Which means, okay, I'll tell you what we will do. Essentially, what you will do is you will break it into q by 2, and exactly as we said, for one term you will use the a over m, whatever that gives, and for the rest it will be q over 1 plus q over 2 plus q over n, and therefore that will be still the same as q log q times the number of such intervals, which is v over q plus 1. And for the one term, what will happen? See, say earlier the one term gave a for every interval. Now this one term will give you a over the b, because the m lies between b and b plus q by 2. And therefore you have to argue a little carefully, but that's what you will get. And that's the type of estimate you will be having here. Okay. And then, is it okay? And then I also need one more modification, namely, whether you write like that or whether you like, okay, let's call P less than or equal to X, because I won't use N for a different sense. Sorry? This is, you mean this? No. You see, the point which I am saying is this 1 over alpha n, if you look at, okay, this 1 over alpha n's are all 1 over 2q apart. Okay? Since 1 over alpha n, that's exactly the reason why I am choosing my n to be an interval of length q over 2, then they will always be 1 over 2q apart, and therefore only one of them will be something. Okay, therefore one of them may be theoretically close to 0. Therefore, I just take A for that. I am taking only the first half, the second half. And then for A, otherwise it will be q over 1 plus q over 2 plus q over 3, or 2q over 1, 2q over 2, 2q over 3, and that will give you q log. And then I said this comment, therefore, this is essentially because your lambda n is by definition log p. If n is a power of p and 0 otherwise, which means the terms corresponding to not corresponding to prime powers is 0, because when n is not a prime power, lambda n is 0. And when n is a prime, this is the same as this. And the differ only when n is a power of prime but not a prime. But the number of such elements which are power of prime but not a prime is little of n. Therefore, you don't have. Okay. Now, what is the idea? The idea is, okay, therefore it's going to be a little complicated, but let's go slowly. The idea essentially for that is somehow write this single sum of a simple functions into a double sum where at least one of the variable would be running over. Yeah, everything will be linear, fortunately for us, because there is a p, and one of the variable will be running over a continuous interval. Therefore, when you write this as a double sum, where one of the variables is running over a continuous interval, I can now use that it is a geometric progression and do the saving from that. Is it okay? And that's all what I am going to do, and that's what the identity which we are going to write. Okay, and that will be slightly complicated. Let's do it slowly. Good. I'm going to multiply these two and write the word value. And now the question is, what is this GS and what is this FS? I will choose my GS and FS in such a way that this is reasonably small and this is reasonably small. Okay? And that is a GS and FS which I am going to choose. Okay? Now, how do you make this to be reasonably small? Again, most of you would have known that the zeta s, 1 over zeta s, is actually given by summation mu n by n power s. Okay, since 1 over zeta s is something like a mu n by n power s, if your GS is chosen to be something like a summation mu n by n power s, then that will be small. And that's exactly what we are going to choose. Therefore, let us assume that GS is equal to summation mu n by n power s, n not exceeding some v. And therefore, at least for large enough s, this of course would be very small. Because for large enough s, this GS would approximate this, and then that is a 1 over zeta s, and that will be 0. And now look at this. How am I going to do this Fs? But again, you know that minus zeta prime s by zeta s is equal to summation lambda n by n power s. And once you know that it is lambda n by n power s, then the choice of Fs is also fixed. I am taking the same V, but of course there is absolutely no reason why you should take the same V in a different context. And this is equal to, now you multiply this minus, see, minus 1 with this and that. Therefore, that will be minus zeta prime s by zeta s minus Fs, which is obtained by multiplying this one with this. Okay? I mean, remember, this is a function which is reasonably small. That's exactly what we want to see. And this, okay, this and this, therefore this minus, this is minus plus, and therefore that is what I have written. Yeah, plus 1 into. And then this and this you multiply, that will be a plus, and therefore I put a minus zeta prime s d of s. The zeta s cancels, and then you have a zeta prime s zeta s. And then this and this it is a plus sign, and therefore I should probably put a minus zeta s gs cfs. Okay, this is correct, except whether I have written the things right, things correctly. Yes, that's right. That is the identity we start with. Okay. The identity which we start with is that you essentially write a small element, and then this things. Okay, and this is small, and this is probably, I don't know whether it is small or not. And now you take your n bigger than v and compare the coefficients of m power s. That's all what you are going to do. Now, when you compare the coefficients of 1 over n power s both sides, and if my n is bigger than v, this coefficient of this is precisely going to be the lambda n. And this lambda n is a small element into something which is a product. And once it's a product, okay, therefore there is another thing which I have to explain. Suppose you have one Dirichlet series and another Dirichlet series. And you want to multiply the two Dirichlet series, okay? You know how to multiply, no? Okay, because this is equal to summation Cn by n power s, where Cn equal to summation AR Bs or S equal to n. Okay, therefore this will be a summation over more variables, and this is a product of two terms. This is a product of three terms. There are more variables floating around, and particularly the zeta s or zeta prime s are nice functions in the sense that there the coefficients do run over an interval. It's all the integers. Therefore, the zeta s is something which you really want to utilize. Then that runs over all the integers, and therefore you can gain something using the fact that you have a linear function and running over an interval. And that's exactly what we are going to do. And therefore, therefore it is easy to say, but then we are just going to write it down. We will write it down. Therefore, now let me write it down. Minus zeta prime s by zeta s minus f of s is equal to minus zeta prime s into g of s minus yes. Some, okay, whatever they are, right. Ca by a power s into zeta s. And this Ca by a power s is really gs into fs. Minus, yeah, okay, zeta s into gs into this. This I am going to write as, what is it I am calling it? Tau a, as they call. Okay. Summation tau a by a power s. This is your zeta s gs minus 1 into that thing. Minus zeta prime s by zeta s minus fs. Therefore, essentially, all the terms on the right hand side I have written as a product of two elements to make my life easier. And now I am just going to compare the coefficients. And when you compare the coefficients, you get a formula for tau n. And this formula for tau n, I claim, is essentially a double sum of the various things, where at least one of the sums would be running over a continuous interval. Therefore, let me write that down. The first minus zeta prime zeta s minus fs, that gives you the lambda n equal to, I am coefficient writing 1 of 1 power s. And you know what is the coefficient of minus zeta prime s? That is log n by n power s. And the coefficient of gs, which is mu n by n power s. And therefore, this will going to be log a ub ab equal to n. Is it correct? No, this you know as log n by n power s. This you know as mu n by n power s. And therefore, that takes care of it. And now this is gs into fs. This is Ca by A power S, 1 over B power S, and therefore consequently that will give you plus summation AB equal to N Ca. Sorry? Oh, yeah, that we have to write the various conditions, which I have not I have forgotten. Yeah, this here mu n, the B is lesser or equal to B. Okay, the Ca also there is a condition, which I will come to that in a minute. And then you know what is this funny thing? This funny thing is a summation Fs I am lambda n by n power s, n bigger than V, and therefore this is again minus tau A minus tau A lambda n lambda B AB equal to n. Hopefully up to that we have written correctly. Let me see. Yes. Is it okay? Now there are various conditions which I have to write as you pointed out, because otherwise I'll have a problem. Okay, and in this summation my GS goes up to only V, and therefore that is the condition which I have written. Now let's look at the Ca. Is there any condition on Ca? The Ca by definition is GS into Fs. Okay, and therefore this is equal to summation some KL equal to A, and I'm getting mu of K, lambda of B, lambda of L, mu of K, lambda of L, and this K is also lesser or equal to V, and L is also lesser or equal to V. Because that's why Ca, which is GS into F of S, which is summation mu K into lambda L with KL equal to A, K lesser or equal to V, L lesser or equal to V, and therefore in particular A will be lesser or equal to V square. Okay? And now let's also write what is my tau A. My tau A by definition is zeta S into GS minus 1. And therefore the tau A is equal to summation over KL. Theta S will give you nothing, and the GS will give you mu L, and the condition will be L less than or equal to B. And KL equal to A. Okay? And this particular number would be C of 0 will be 1. And therefore that 1 is subtracted. Therefore that won't come. Okay? And further, this number you can write if you want as L dividing A, L lesser or equal to V, mu of L. And when you are writing L dividing A and L lesser or equal to V and mu of L, and if this A happens to be lesser or equal to V, if this A happens to be lesser or equal to V, then this condition is redundant, because only L divides A, it will be lesser or equal to V if A happens to be lesser or equal to V. And once A is lesser or equal to V, this condition seems to be redundant, and therefore you have only summation L dividing A mu of L. And we know summation L dividing A mu of L equal to 0. Therefore, consequently, your tau A becomes 0 if your A happens to be lesser or equal to B. Therefore, your A happens to be bigger than or equal. And your lambda B also bigger than or equal to B. Therefore, with and your B is also bigger than N. And that is the identity we are looking for. Therefore, the identity which we have is lambda n equal to summation log A mu B plus summation CA minus summation tau A lambda B, where the various conditions with AB equal to 1, B lesser or equal to V in the first case. And then A is lesser or equal to V square and A lesser or equal to V, B. Is it okay? And now I don't need any more. But I am not interested in lambda n. I am interested in summation lambda n E alpha n. That summation with the n lesser or equal to, let us say, some oh God, getting out of numbers. N lesser or equal to P, I want to sum up and get a non-trivial estimate. Okay? But this formula is valid only when n is bigger than V. Correct? Because the left-hand side was minus zeta prime s by zeta s minus the corresponding thing. Therefore, this formula is valid only for n bigger than V, and therefore I can use this formula only for n bigger than V, which means obviously I break it into two parts, n lesser or equal to V and n bigger than V. And n lesser or equal to V, even the trivial estimate will give you O of V. And even let me give you a secret. Ultimately, I am going to choose my V to be n power 2 over 5. And therefore, the n lesser or equal to V is a trivial estimate itself is O of V, I don't care. And therefore, I can use this for n bigger than V. And therefore, what I have is V lesser or equal to n lesser or equal to V. That's what I want. And I have a formula for lambda n. And I am trying to look at V lesser or equal to n lesser or equal to P. And then substitute this formula. And then I want to see what happens. Okay, therefore, let me just substitute the formula and then we will have a break and then come back and simplify. Therefore, when you do that funny thing, first one, this will be a log A and there will be a mu B, and then you have a E of alpha n, which is E of alpha AB, because n is AB with the B lesser or equal to B. Plus summation C of A, E of alpha AB, and with the A lesser or equal to V square. Minus summation tau A lambda B E of alpha AB with A bigger than V and B bigger than V. In this completed expression, I think I have written it correctly so far. Yeah. Sorry? Here. Lambda A, tau A, lambda B, E of alpha AB with A bigger than B. Oh, this is a double sum. Okay. Oh, yeah, I have not written, but that's a double sum of A and B, yes. Okay? Therefore, now we have written. And now the only thing which I have to say is that all these sums, at least one of the variable lies over in interval, and therefore I can do some gaining. Okay. Therefore, let me, since I need more place, let me write what I have written. Tau A is equal to summation mu L, L less than or equal to B, L dividing A. Yeah, and that CA is equal to summation UK lambda L, where K is also less than V, L is also less. Okay, therefore now we have written this sum which we wanted, which theoretically was not, the n was not going over an interval, but then we have written as a double sum A and B. And if I can prove that it in at least one of them it goes through an interval, because fortunately for us things are linear in both A and B, we are happy. Is it okay? Now, I made yesterday one comment which I may have to sort of withdraw, which says that if you have a E of a linear function over an interval, that's the only case which we know where there is a saving, for the simple reason that I can use that it is a geometric series. Okay, but and then we saw that in Waring's problem, in Weyer's inequality, if it's a kth power, then by squaring again and again and again, we can reduce the degree and make it linear. But there is one more case where it is true. The one more case, oh God, I'm using F for so many things. This is essentially because there is something called Abel's partial summation, which all of you would have known, and therefore you have a monotonic function. Then this monotonic function can be essentially taken out, and then you still will have an interval. And there are still two advantages. Number one, still n will be going through an interval, but we don't know whether the same interval, but maybe in a different interval. And there is no absolute value. That's what Abel's partial summation tells you. That if you have any function and then you have an Gn and you have a Gn, then and if this Gn is monotonic, this all of you would have seen. Correct? And if this Gn happens to be monotonic, then you can essentially take the maximum of the Gn outside, and inside you will still have the function. You need not put an absolute value. It still will be running over an interval. Maybe a different interval. But for us, it doesn't really matter whether it's running over the same interval or different interval. That it runs over interval is what is important. Good. And now let's look at these sums. One sum I will do, and then the rest I will leave to you. Therefore, this, let's call S1 minus S2 minus S1 plus S2, no, it should be minus S1 minus S2 minus S3, that's what everybody writes. Now look at this S1. In S1, if I put the A summation inside and the B summation outside, and then you put a log A here, and then you have a AB alpha here, and then you put a mu B here, okay? And this A summation is running over an interval. And in fact, the very fact that this AB is lesser or equal to capital P, and therefore, therefore this is one more condition, AB less than or equal to capital P, and therefore which means A runs in less than P over B, and everywhere of course AB runs over capital P. So that's why the B I didn't write. And this A runs over an interval, and the inside summation is linear, and therefore I can gain by using the fact it's a geometric progression. And therefore this number is less than or equal to summation B minimum of P over B 1 over B alpha. Good. And this is exactly what we said. Okay, well, anything like that, you can now break it into Q over 2 and sum over every interval of Q over 2 and sum it up. Okay. Therefore, this is done. Now let's look at S2. In S2, I mean, this is what in the literature is normally called the type 1 sums. There is one of the variables will have only that function and therefore you can manage it. Only if there is an intermix, you will have a problem. And S2 is also clearly a type 1 sum because there is no function of B floating around as a coefficient. Since there is no function of B floating around as a coefficient, you can write summation over A, CA, summation over B, AB alpha. And A goes up to V square, therefore B goes only up to P over V square. Sorry? This AB? Okay, let's see what are the conditions on CA. This is V square. Yeah. Oh, N is bigger than V and therefore AB is bigger than V. Yeah. And the only point which I have to be very careful is that this B lies over an interval and that should be true for any given A. Okay? And then of course I should know, therefore this is summation A over A, summation over B, AB alpha. I have no problem. And now the summation over there will be a CA. And I just need to know some bound on this CA. Okay? But CA, each of the terms are bounded. When I say bounded by powers of log, which I don't care. And the summation is over all possible K and L with the KL equal to A. And therefore that is bounded by the divisor function. And in L1 norm, divisor function is also bounded by log. I don't even care. Good. And therefore this is also something where you can make a gain. And your problem comes essentially in the type 3 sums. The type 3 sums, the S3, which is the type 3 sums, and this has a tau A, and then it has a lambda B, and tau A is not monotonic, lambda B is not monotonic. Therefore, by writing A first or B first, we are not going to do anything. Okay. Therefore, now somehow we have to handle that, and that's exactly what we are going to handle now. Good. S3 is less than or equal to summation over A, tau A, summation over B, lambda B, E of AB alpha. And the tau A also is essentially bounded, remember. I mean, when I say bounded, I am always ignoring a fixed powers of logarithm. Therefore, this is also bounded and this is also bounded. And now I can probably use Holder's inequality. This is okay. I should have done something more. This is a little tricky. What we do already is in this particular case, okay, A and B are running over intervals, but on the other hand, it is definitely easier to make a binary division first before we do anything. And therefore, let us assume that we are only looking at A less than or equal to A less than or equal to 2A and B less than or equal to B less than or equal to B2. And then finally, somehow our AB less than or equal to B. Okay, because otherwise the ranges would give you problem. And therefore, let's do the binary business. And once you do the binary business, this is less than or equal to A. Because as I told you, I am forgetting all the logarithms and therefore tau A is bounded and therefore summation over A, tau A square is equal to A. Therefore, the tau A now has completely disappeared. And now you have a summation over A, summation over B1, summation over B2, lambda B1, lambda B2, E of A into B1 minus B2 into alpha. Okay, and therefore this is less than summation over A, summation over B1, B2, and then summation over A, E of A of B1, B2 minus alpha. And now finally I have a summation over A. This summation is over in the interval. I do gain out of that. And therefore this is equal to summation over A, B1, B2. Oh, that's a lambda B1, lambda B2. But I put an absolute value now. If I put an absolute value, I can even forget the lambda B1, lambda B2 because they will be outside and I am always forgetting a fixed powers of logarithm. Okay? Since I am... and now this is equal to summation over A, summation over B1, B2, some minimum of A into 1 over B1 B minus B2 times alpha. And now we know how to sum it up. Okay. Therefore, essentially what we have done is we had a summation originally over a non-interval, and that simple summation we wrote as a double summation. And in S1 and S2 or EC, they were type 1, which means already by putting the which variable first and which variable second, we already had a summation over an interval. But unfortunately, in the third, there was a problem because there were coefficients depending upon A and B. But on the other hand, you can use holder. And if you know the L1 bounds for this, which is just a fixed powers of logarithm, which we are always ready to ignore, and then you get that. Is that okay? And therefore, that I will leave it as an exercise, how to do that. And therefore, I will finally state the theorem. This idea is useful not only when you are summing a lambda n E n alpha. This idea is useful when you are summing up summation lambda n of anything else also. You can always do the things. You write the lambda n's and then put that in a summation. And finally, what it gives you is essentially E n alpha, n less than or equal to n in this case, sorry. Therefore, n less than or equal to any 2 equal to is equal to that q divided by little q plus that q raised to the power 4 by 5 plus q power half. If alpha minus a over q is less than 1 over q square. Good, this is it. This square root comes essentially from the S3. S1 and S2 would be even smaller. And in S3 I have squared it and gained a q. But then, since I gained a q only after squaring it, therefore I really gain only a square root of q. And again we saw that if your alpha belongs to the minor arc, you can assume your q to be bigger than p, because q less than p already goes to the major arc. And therefore, and p is a power of log n. Therefore, we have gained a power of log n power 25 over a trivial estimate. Okay? And remember, you can always gain a power of log n over a trivial estimate as long as your power is strictly bigger than 2. Because if your power is strictly bigger than 2, 1, 2 I can keep inside, and the rest I can take outside. And for the rest, I can use false identity and gain at least a power. And for that too, the Parseval will give you 1. And that's all the gain which you need. Therefore, if you can somehow get the power to be bigger than 2, then you can do something. But if the power is less than 2, then you have a problem. Okay? Equal to 2, then you have a problem. And that is why now I am going to say something which is very difficult, which I am not going to cover, that even in the binary, if you want the minor arc estimate, which is modulus of f of alpha whole square over the minor arc, it's called E of n. Then by Parseval, you can essentially get up to any x. I mean, how do I do the Parseval correctly? Where did I have this Parseval business? Oh God, we had it. Yeah, well, okay, what will Parseval tell you? Therefore, this is En, and then you have a summation over. Yeah, okay, Parseval should give you power 4. And how do I get the power 4? I see. I thought I had an idea how to get a power 4. I will. Good, I will probably make a comment a little later. But you can use Parseval to get a power 4, which means essentially you can get that the summation En square is equal to x over. Oh, En is the main term is around n, therefore that will be n square, and therefore x power 5 by some power of log n. In other words, you can prove that the En is smaller. Okay, that's the theorem. The minor arc estimate is smaller than the major arc, except possibly x over log x over 25 elements. up to x. This is the theorem of Eastman. That is, you can prove that the minor arc is really smaller than the major arc, not for all L, but with a few exceptions it can be. Sorry? This one? Yeah, this one I mean I will do that little later. Sorry? No, what I'm saying is that the major or minor arc will be smaller than major arc except for an exceptions. And this is all what practically would come from what we have done. And therefore it is really surprising that when Montgomery and Vaughan proved an exception of the form x power 1 minus delta. And since we do not see any hope of proving binary Goldbach in the near future, because we don't have the tools, therefore practically the research work is going on to see getting better and better delta. Okay, and the delta which Montgomery and Vaughan got was probably 0.02 or something like that. I don't remember. Now probably we know something like a 0.1, and Belog claimed something like a 0.3. Okay, but that's where the research in Goldbach is not in proving anything about the Goldbach, but in proving that the exceptions are small. Okay, which of course needs something on the zero density estimates, zero free regions, and so on and so forth. Okay, I stopped there essentially because there is at least one more theorem which I want to do and which I will not be able to do in 1.5 hours. Therefore, I will take some 15 minutes to just do the theorem of Davenport. Capital G4 is 16. That every number is a sum of 16 fourth powers. Even that I would not be able to prove, but at least I can give you what's the basic idea. And this basic idea, at least this I hope to prove. In the first lecture, we proved that if S is bigger than 2 power k, then you have an asymptotic formula. And then to reduce the all the way the 2 power k to something like a k log k by Davenport is a fantastic achievement. Means somewhere you say 2 power k to k log. And therefore, what is basically the idea? The basic idea is essentially the parseval. Again, using the parseval. Therefore, suppose I want to prove 16 fourth powers, for example. Okay? And then, of course, the major arc you would expect whatever you want. As we have already seen, that the major arc you will always get n power s over k minus 1 without much difficulty. Because that's the contribution to be expected. And what you are always, that is, and with the n capital N equal to 1 over 4 in this particular case, this is n power s over 4 minus 1, and which is p power s minus 4. This you will get with no problems. And therefore, as far as the major arc is concerned, you lose a power of 4. And therefore, that power of 4 is what you have to gain in the minor arc. Okay? You see, the problem is that you cannot gain in the minor arc a power of 4 essentially because, again, if you take the full 16th power, for example, you can get a power 4, saving of power 4 from Hua. Because 2 power k, if you go up to 2 power k minus 1, you can choose a k. But then you will have nothing else to choose. But on the other hand, if you try Whale, it chooses only 1 over 8. And that saving, therefore, total saving will be only 2, which is not good enough. Okay. Probably you can use this Parseval. Parseval will save you 1. Okay. But you don't, that is not good enough for you to save. You need to save more. Okay, therefore, let's try the following trick. Let's try the following trick. You take 0 to 1, you write f alpha power 6, and then another f alpha power 5 whole square, and then d alpha. And the 6 I want to use for the major arc contributions. And this funny thing I want to write as V alpha. Therefore, V alpha is f alpha power 5. And now this m goes up to actually p power 5. And therefore, consequently, you have a 0 to 1 f alpha power 6 into V alpha whole square d alpha. And this f alpha power 6 you really use for the major arc. And for the minor arc, you have this f alpha power 6, you take it out using Whale, gaining something. And this V alpha square, now the Parseval should save you something like a p power 5, because the sum runs over the element of p power 5. Okay? And then you should be very happy. But unfortunately, it doesn't work. Unfortunately, it doesn't work simply because when you use the Parseval, what you will have in the right-hand side is summation Rm whole square in the estimation. You will save a p power 5, but then you will have a summation Rm whole square, and the Rms are normally very big. And once the Rms are very big, therefore the estimate will be still bad. Is it okay? And therefore, now let's try to do something else. You don't write the V alpha, then you write a U alpha equal to epsilon m em alpha, where epsilon m equal to 1 if Rm is bigger than or equal to 1 and 0 else. Therefore, I replace the coefficients, the big coefficients Rm by 1, wherever I have to. If the m can be written as sum of 5 fourth powers, I put a coefficient 1. And if m cannot be written as sum of 5 fourth powers, I put a coefficient 0. Okay? Therefore, the coefficients become very small now. And then hopefully Parseval should gain. Is it okay? Therefore, that's all exact. And the very first time somebody was asking whether I can put some weight there somewhere to do this calculation simply. And this is the only thing which we know. We can put this weight. And therefore, now let us study about this weight for a minute. Therefore, now what I am looking at is this summation f alpha power 6 u alpha whole square d alpha. This is my I, and this u alpha is equal to summation E of u alpha, where u runs over u, which is those m's such that u is a sum of 5 fourth powers. That is, I have reduced And my U now I don't allow up to n, I only allow up to, let us say, n over 10. A little less. It won't change anything in the order. Now let's see what is a major arc. The major arc is 0 to 1, f alpha power 6 into E of minus of n minus u1 minus u2 alpha d alpha summation over u1 u2. The u alpha square I have expanded. What is this? Now in the major arc, then what is this integral? This integral is the major arc contribution of writing this as a sum of sixth power, as a sum of 6/4 powers. Therefore, I am trying to write n minus u1 minus u2 as a sum of 6/4 powers. And I said that my major arc will not give you any problem even if S is small. And therefore, this contribution has to be bigger than or equal to summation u1 u2 n minus u1 minus u2 power s over k minus 1. Because always the contribution is n power s over k minus 1 for the major arc. And now, since I have chosen my u1 and u2 to be less than n over 10, that is the reason why I chose this. This is of the same order as n. This is of the same order as n, and therefore you have an n over 6 over 4 minus 1 gives you a half, and then you will get a mod u square. And on the other hand, when you look at the minor arc, this f alpha power 6, you take it out. Will give you a bound p power 7 over 8. And for that u alpha square, you use Parseval. And when you use Parseval for u alpha square, you gain a u. And therefore, this is less than or equal to p power 42 over 8 times cardinality of u. Now, if you can say something about the cardinality of u, you should be able to say hopefully that the major arc is bigger than the minor arc. And that's exactly where we will start in the next lecture for the major arc and minor arc. Is that okay? Okay, let's stop there.
Okay, thank you very much. Are there any questions?
I have given up the fact that I have lost asymptotic formula. You are absolutely right. And therefore, you can always ask the question, what are the things, which level you can really get it? You can get an asymptotic formula, and that is called G1, I think, if I remember correct, by Vaughan and Woolley. And that is again one very interesting aspect of research. No, without getting the asymptotic formula, I have put that everything is representable. But whether for the 16 you will get an asymptotic formula or not, is that what you want to know?